Hi, this is Brian, and along with Samson, Marion, Stephanie, Willie, Alana, and Professor Yao Zheng, we shall present SIENNA, a insider-resistant, context-based pairing for multimodality sleep apnea test.
In America today, millions suffer from obstructive sleep apnea, or OSA, an airway muscle related breathing condition that causes involuntary respiratory cessations during sleep. Poor treatment can cause a myriad of negative health problems. However, the typical diagnostic procedure, an in lab polysomnography, or PSG, commonly referred to as a sleep study, can be costly, intrusive, and are scarce, requiring the patient to be in lab overnight. The alternative, at home OSA screenings, provide convenience and are economically advantageous, but the device pairing they utilize can be vulnerable to wireless exploitation and testing fraud. The at home multimodality OSA screening system we utilized has three modules. One, a respiratory belt that straps around the chest, measuring changes in thoracic circumference from respiration. Two, a physiological radar monitoring system, or PRMS, that measures the phase shift of reflected signals from the patient's chest movements. And three, a mobile OSA app that connects to and collects data from the sensing modalities. The issue with at home OSA screening comes with its pairing vulnerability. The belt is typically paired with the patient's phone by a medical technician during the clinic visit. The PRMS, however, is paired without supervision at the user's home. This unsupervised pairing process could be subject to exploitation from a non compliant user. Our design goals were to pair the two devices with zero human interaction in such a way that the process is protected against a co located adversary. What distinguishes our adversary model is that the system's legitimate user could be an attacker. They may seek to eavesdrop the pairing between the PRMS and their phone to extract the security key, decrypt, and review the data before a doctor examines it. They may also leverage the eavesdrop key in order to transmit false data to the mobile device, manipulating the testing outcome.
Our solution, Insider-Resistant Context-Based Pairing, or SIENNA, is a system for device pairing that is resistant to both fraud and eavesdropping. SIENNA incorporates four elements: JADE ICA, level crossing quantization, fuzzy commitment, and friendly jamming. JADE ICA, or Joint Approximate Diagonalization of Eigenmatrices for Independent Component Analysis, is used to separate independent breathing patterns from a mixed source signal. JADE ICA uses principal component analysis to find a matrix with orthogonal column vectors, or a whitened matrix. Then it rotates that matrix so that the rows are maximally independent. The result is a demixing matrix that can be applied to isolate the independent sources with no prior knowledge of either one. Level crossing quantization is a technique for converting the analog breathing patterns extracted by JADE ICA into a binary signal by producing a unique binary code for each signal level at discrete time intervals, as seen in Figure 6.2. Fuzzy commitment is a scheme for committing a key from a secret value so that it can be compared with an opening commitment and revealed only if the opening commitment is within a set threshold, rather than requiring an exact match. The security in this approach is based on the hardness of concealing, or the difficulty of guessing the secret value, and binding, or the difficulty of retrieving the secret value with an incorrect opening feature. Using 128 bits for the secret value and 256 bits for the hash function, we find the hardness to be comparable to SHA-256 encryption. Friendly jamming is a means for wireless communication that is resistant to eavesdropping. Commitments are converted to OFDM symbols and transmitted in duplicate. The receiver randomly jams one of each pair. Since an eavesdropper cannot distinguish between jammed and unjammed symbols, it is unable to recover the original message.
SIENNA was tested using a customized millimeter wave radar from TMY Tech, specifically their B-Box and up-down converter. This setup uses a 28 GHz OFDM radar controlled with National Instruments USRP 2974 and interface through LabVIEW, along with the Pneumotrace 1132 respiratory sensor. During testing, the Android device communicates with our host computers through BLE and is connected to our LabVIEW implementation, which executes the modality switching and data logging. Our eavesdropper/spoofer was based on a BLE device using Kismet and Ubertooth. For testing purposes, we had two testing setups, one indoor and another one outdoors. The indoor setup uses two twin beds, whilst the outdoor setup uses beach mats and umbrellas. Both setups tested in a similar fashion with the subjects wearing the respiratory sensor and half a meter below our millimeter wave radar. Each experiment lasted approximately 1 hour, during which we toggle modality switches and adversarial attacks through our BLE eavesdropper/spoofer every 10 minutes. During each experiment, a third party executed the modality switches and operated their computer running the Ubertooth. The packets transmitted by the OSA application, the chestband, and the millimeter wave radar were identified based on their Bluetooth device addresses obtained prior to the experiment. To implement eavesdropping attacks, the host codes records the packets containing fuzzy commitment and hash values of new keys from the modality switch. The spoofing attack was done with a attacker-generated compliance tracking data encrypted with the deduced key, which was transmitted at higher power during data upload toward the Android app, in an attempt to manipulate the latter into accepting the fraudulent data, which was verified during offline analysis.
The breathing signature was quantized by utilizing LabVIEW to generate binary fingerprints. The breathing signature is a combination of complex thorax motions due to the respiration and heartbeat movements within 0.5 centimeters to 0.05 centimeters. Figure 10.1 illustrates the quantized data in the time domain of movement when the subject is at rest. A quantization step size of 0.05 centimeters at 10 sample rates per second was the best to preserve 5 movements. The quality of the binary fingerprints were evaluated based on the Hamming distances between fingerprints observed by different modalities. Human subjects are distinguishable based on their inhales, exhales, and breathing depth, which can be directly translated to Hamming distances. Figure 10.3 illustrates the similarities of same subjects observed by different modalities. It demonstrates that the average Hamming distance per bit between fingerprints is around 63% within the first 6 seconds. Meanwhile, Figure 10.4 illustrates the similarities between different subjects observed by different modalities. The average Hamming distance per bit between fingerprints is below 5%. Overall, SIENNA can be set around 70% to allow accurate patient tracking during modality switches. The security of fuzzy commitment is measured by the randomness of commitments. Our results show that the entropy per bit drops nearly by half due to the redundancy of the human respiratory motion's cyclic character. SIENNA's performance against eavesdropping and spoofing is evaluated by comparing the bit error rate BER at the receiver versus the aggregated BER at the attacker's side. Our experiment showed that the jamming signal could suppress the attacker's BER to roughly 50%, which would render an undecodable message for the attacker.
In conclusion, we introduced SIENNA, which stands for Insider-Resistant Context-Based Pairing, a secure pairing scheme that leverages breathing patterns through the use of fuzzy commitment, friendly jamming, and JICA techniques. We presented an overview of our security analysis and evaluation, which consisted of 3 attack scenarios in which the attacker has no knowledge of, has a partial knowledge of, or has a complete knowledge of the user's breathing fingerprint. In addition to being robust within a noisy environment with multiple subjects, our results showed that SIENNA can protect the security key during the pairing process in each of these scenarios. We'd like to give a special thanks to Dr. Yao Zhang, Dr. Meng Li, Drs. Olga and Victor Lubecki, and Yanjun Pan for mentoring this project, as well as TMY Technology for their support and equipment. This work is also partially supported by NSF and ARO. Thank you very much for tuning in, and have a good day.